Hey everybody, our next information that we need to talk about would be Chapter 14, which deals with sound, specifically sound waves and beats. So sound waves are actually longitudinal waves. We talked about different types of waves in the last lecture. And one of the things we look at is we look at our waves are actually longitudinal. They're meaning they're going to be having the sound being compressed and expanded. So here you see if you have a speaker that's going to be generating, it's going to be moving sound waves in and out. And you can just follow those along. If you see a path, it'll just continue moving along. So really sound waves are just longitudinal, where you have waves that are going to be compressing and expanding the air. And that's actually what creates the sound that you're actually going to hear. So sound, people say the sound moves really fast. Sound moves at 343 meters per second, or about 770 miles per hour. So that means it's going to be moving very, very fast. Now granted, that's the speed of sound in air, and it does depend on the medium and the temperature here. So if you see this information right here, you got it at 0 degrees, at 25, at 100. You can see that as the temperature of air gets bigger, the speed of sound actually gets bigger too. And in different types of mediums, it's going to be moving faster also. So in aluminum, it's going to be moving much faster at 5,000 meters per second. So it depends on the medium that it's in, and that'll definitely change how fast sound moves. So in a quick little question there, it says, sitting in an outfield bleachers 170 meters from home plate, you see a batter hit a ball. How long after you see the hit will you hear the sound? And you've probably experienced this before, where you see something happen, but you don't hear it for quite a while, like in the case of fireworks, for example. What we can do here is we can actually just do a quick little distance versus time equation. So we know that speed is distance over time. So we know the speed is 334 meters per second. Our distance is 170 meters. So our time is what we would actually be solving for. So if we rearrange that and solve for the time, we get a time at 0.51 seconds. Right? So that's where that delay comes from, as you're hearing something that's going to be happening, where you'd see it and then you don't hear it for quite a while after that. You may have also heard of that 5-second rule for lightning and thunder. For example, if you see the lightning, you can count how many seconds it takes to hear the thunder. And as a rule, for every 5 seconds between the lightning and the thunder, the lightning is going to be 5 miles away. So if you see lightning, you count to 5, and then you hear the thunder, you know that was a mile away. If you count to 15, then it would obviously be 3 miles away. So it's just one of those things, if you look at for the speed of sound, that you can figure out. A couple interesting things here. When you talk about sound, number one is it doesn't matter what sound you have, it all moves at the exact same speed, which would make sense because you hear sounds, you hear them all happening at the same time. It doesn't mean that a flute sound moves faster than a trumpet sound, for example. All sounds move at exactly the same speed. And that sound, that frequency that you actually hear for a sound, is what you perceive as the pitch. And the higher the frequency is, the higher the pitch is. So flutes have a really high pitch, meaning they're creating generally very high frequency sounds. Conversely, if you have a tuba, it's probably going to be making a pretty low frequency sound, so therefore tubas have a much lower pitch. So when you talk about the speed, that's not related to what the sound is. All sounds move at exactly the same speed, but different sounds can have different pitches. So if you have a frequency that's really, really high, it's going to have a really, really high pitch. Some other things as far as the sound goes, different sounds we can hear. We can hear sounds between 20 hertz and 20,000 hertz. That's a pretty wide range. 20,000 hertz would be a really high pitch. The 20 hertz would be a really low pitch. But there are sounds less than 20 and above 20,000. And below 20, those are called infrasonic. And above 20,000, those are called ultrasonic. Bats, like it says, they use ultrasonic waves to echolocate. So they're using a really high frequency sound to be able to work. Where elephants can use really low frequency sounds to communicate. So there's definitely different uses of the different sounds and the different frequencies that sound actually is going to have. So one of the things, when waves start to overlap, they can interfere constructively. So if you ever heard sounds like when a band is tuning, for example, you'll hear the sound coming in and out. Those are actually called beats, and it goes right along with the superposition of waves. As they start to overlap, you start to hear these different warbles of sound that are going to be present. I know it's not a real scientific word, but that's actually what's going to be showing up there. this will come up for us. We can have some different sounds that are going to be present. So right here we're going to have one ear at 500 and the other one at 530. So you'll be able to hear those different frequencies coming in and out. So you should be hearing about 3 beats per second because the frequencies are 3 different. If we put this up to 510, you should hear the beats a lot faster. And if we drop that down to 501, we should just hear maybe 502. So those perceived beats are the difference between the frequencies that you're actually going to be hearing. So the beats are those sounds where you have the sounds that aren't quite in phase, and in turn you'll hear those different sounds that are going to be taking place there. So if you want to hear them for yourself, you can go online and just search for a beat generator. It's a pretty easy thing to find. There's one right there, onlinetonegenerator.com. Is one that you could use. You can find lots of other ones too. Into section 3 and 4, we'll talk about the Doppler effect and the human perception of sound. So the Doppler effect is maybe something that you've heard of before. You may not have known what it was, but you definitely know what it is. So Doppler effect is when the pitch of a sound will change. For example, if a fire truck is coming at you, you'll hear the pitch getting higher. When it goes away from you, you'll hear it getting lower. In this example right here, you have your moving sound source, and as it's coming at you, you can see the sound waves are closer together. That would indicate that your pitch is going to be higher. As it's moving away from you, the sound waves are getting to you less often, therefore the pitch is going to be lower. So if you just watch that a few times, you'll see as the red dot is coming towards the right, there's a lot more waves, a lot more lines. Those are representing the sound waves. Once it gets past, then the sound wave is going to be going down. So that would be the Doppler effect. It's something that you hear quite often as the sound waves are moving past you. Our perception of sound measures the intensity. Like we'll often know that a sound is loud or a sound is quiet, but sound, the intensity of it will change with distance. So as you have a sound that's really loud, the closer you are, the louder it's going to be. That's why if at a concert you're standing right up next to the speaker, it's going to be really loud and almost unbearable perhaps. Where if you're a long ways away, the sound's not going to be near as loud. So that sound is based on how close you are to the source, which is also looking at the amplitude. The bigger the amplitude, the louder the sound is going to be. So when you think about a wave, the sound waves that are there, the higher the amplitude is, the bigger the sound is going to be. And what you might have heard about before with sound waves is something called the decibels. And there's definitely a decibel level. It's a way of measuring the intensity of the sound. So our decibel is actually the unit for loudness. It doesn't have a unit. We just say that a number is so many decibels. So what happens is as you look at your sound, it says up there at the top, it says if one sound is twice as loud as another, its intensity is 10 times greater. So if you're doubling the loudness, how loud you perceive it, the intensity is actually getting 10 times greater. So to think about that a little bit, it's kind of a difficult thing to understand, but if you would go from 70 to 80 decibels, the sound would be twice as loud, but it would be 10 times more intense. If you went from 70 to 100 decibels, you're increasing 30 decibels, so the loudness is 6 times louder, but the intensity is 1,000 times greater. That's why it gets really important as sounds get louder to wear ear protection, because that intensity is what does the damage, what can actually do the damage to your ears. So keep in mind, it's not that the sound is just getting louder, the intensity and actually the power of the sound is getting louder too. So keep in mind, decibel are what we measure sound levels in, and the louder that sound is, the more intense the sound is actually going to be. Just some examples of some different things. If you have a whisper, that'd be around 30 decibels. A car or an alarm clock is around 70 decibels. You get all the way up here to a rock concert at 120 decibels. Right? So if you compare people just talking at 60 decibels to a rock concert at 120 decibels, you're talking about 60 decibels different. That is significantly going to be significantly louder, and powers of 10 that are going to be much more intense. So that sound is really increasing, as is the intensity of the sound that's going to be coming out of it too. So that's really why it's important to keep those ear protections in your ears when you're actually going to be doing something with really loud sounds. Next thing here, frequency in music, because obviously music is made of frequencies of sound, and they actually have an exact pitch. So if you've ever been in band and you've been tuning in instruments, well, the reason you can tune them in is because that pitch has a particular tune. So middle C on a piano is at 261.7 hertz. That's what's defined as middle C. And what's happening as you're moving along here, if you go one octave up, which means you increase from one octave to the next, basically you've doubled what that frequency is going to be. So 261.7 is going to be middle C. The next octave up is going to be 523.3. So you just keep increasing each of those by doubling it as you would go along. The 2 octaves up would then be going 4 times the 261.7. And it's just kind of interesting here, not that you truly need to know it, but it says notes in between are separated by multiples of 2 and 1/12, because that's how much each note is going to be separated on there. So just something kind of interesting for you. Not super important that you have to memorize that, but there is a relationship between the frequency and the music and the pitch and the wavelengths that you're actually going to be hearing. So obviously, when you would go from middle C, that's going to have a 261 hertz to the 523 hertz. Since the frequency is going to be getting bigger, the wavelength would have to be getting smaller. So a sound, we're generally not measuring wavelength. We're generally looking at the frequency. That's usually what sound is going to be measured in. Where light is generally measured in a wavelength. So keep in mind when we're looking at different types of waves, it's important to keep in mind how we measure it and what those measurements mean. If you have any questions, let me know. That is the end of this lecture.